everyone, and welcome to the last talk of the day. And it's a special highlight because I'm really glad to introduce Noah Husser, who's one of the authors of Probe RS, really a cornerstone of the embedded ecosystem in Rust. I'm so glad that he's going to talk about that as the final talk of the day. Thank you.
So, good evening, everybody. I hope you enjoyed a great day of Oxidize with a lot of interesting talks and have some energy left to spare for my talk, Probe RS, your Embedded Tome. So, very short introduction. My name is Noah Husser, better known as Yateki on the internet. I'm a Swiss software engineer, and I work at my own tech consultancy, Technocrat. We're doing all sorts of electronics and software, so from power electronics to server backends. And we try to use Rust as much as possible, more and more. And in my spare time, I like doing all sorts of sports, such as jiu-jitsu, which I especially like. So let me talk a little bit about embedded development. So when doing embedded development, I guess most of you have used some tools I have listed here. So there's lots of probes and on-chip debugging tools that can talk to those probes and your target, and you use them to flash an ELF binary to your target or to get debug information from your target. So this sounds great at first, and it is great sometimes that you have such a huge selection of tools from which you can choose. But there's drawbacks, of course. So the ecosystem is very stiff. So oftentimes you don't really get to choose each tool, but there are a chain of tools that you have to use. And many vendors ship their own tool set, such as Eclipse, which then is GDB based again, and they all add their own flavor, and you're kind of stuck with those tools. And in the last 7 years, I've been doing embedded development. I have always been using those tools, and for every project, it was a different tool, and you always have to relearn stuff. And even in the open source community, some tools require configs you don't really understand, and it was always kind of magic to me. And then in 2019, shortly before the first Oxidize, where I met a lot of folks that actually contribute now to Probe RS, I started looking into those things because I was kind of disappointed with how the setup went. Because in Rust, we have those great tools such as Cargo, for example, that really make development nice and easy. And I think embedded development should be fun too. So we have many cool tools with a lot of features, but they're not really nice to use. And we tried to change that. So in the traditional debug setup, you have a target here at the bottom that is a CPU of a different architecture than your host at the top, where you write code on. And those two can't really speak with each other. So you need a debug probe here in the middle that translates sort of the protocol that the target CPU uses. And this is mostly SWD or JTAG, and this is a standardized interface, which is different for each architectures. Sure, some share a common interface, but this is basically defined by the architecture, and it is well documented too. And then on the host side, the debug probe mostly uses a proprietary interface. There is some standards defined by ARM, but not everybody uses them. And it's really tricky to get this right because not all debug probes use the same level of abstraction. So some are higher level interfaces and some are lower level interfaces. So this is kind of a tricky point to get this right. And of course, we have been writing Rust software on the target in the form of firmware for a long time. And now with Probe RS, we have also implemented those interfaces in Rust 2, SWD and JTAG, and of course the host side interface to talk with the probe. And of course, we have written a lot of software that is running on the host, so this is Rust 2. And the only missing piece really is the probe, which is still proprietary. So, and on the host, of course, there is a whole stack of applications. I have listed them a few slides earlier that you normally use. So traditionally, you have a target here at the bottom again, And then in the middle, you have a debugger in the form of GDB mostly, at least for open source embedded development, but many manufacturers actually ship it inside their Eclipse-based distribution or the likes. And then you have a UI on top. Traditionally, I know it from Eclipse, but many folks nowadays, for example, use VS Code, of course, such as you would know it from normal x64 development. But in between those three components, you have on one side the GDB stub, which is the GDB server. And it basically translates the GDB commands such as read memory, write memory, etc., to commands the target understands and yields the data back. So this is sort of the probe driver, right? And every probe manufacturer ships their own flavor of GDB stub. So you always have the interface is always similar, but for example, flashing a target is not always the same for each and every target. And the same is on the other side, you have the GDB MI, the machine interface, which sort of provides a machine-readable interface to the GDB UI that, for example, an editor can use to actually interface the debugger. But then again, the editor needs another plugin which speaks this machine interface, so you get all these different interfaces and this sort of layer cake, which can be unstable at times. So what we are aiming for is eliminating all those interfaces that can cause friction and provide one single blob in the middle here named as server and also marked with a Rust symbol because we already have written that in Rust. Which is sort of the missing link between the UI and the target. Because many editors nowadays provide at least some sort of UI to debug. And there's also standardized interfaces to implement this. So this simplifies the entire chain and should remove a lot of problems. So here are some of the probe RS benefits that we can get or that we try to achieve. So as I said, we want to have an editor of our choice. For me, this would be ideally VS Code. And we try to make ProbeRS as a library such that you can use it or that you can just put a thin layer of UI on top or a little server such that it can interact with your own tools. So you don't have to write any weird script or something, but you have a clean Rust API. And we try to document this properly. It's not always the case yet. And what's very important too is that it is streamlined. So for example, in OpenOCD, you have for different architectures, you have different commands to read memory, for example. And we try to not make this different because the user is mostly interested in executing a command on the core, for example, read memory. And this is always the same from a user perspective, right? So the user shouldn't be forced into using different commands and learning different interfaces, but they should just need to do a memory read, right? Yeah. So, and for our binary tools and also library usage, we strive for a simple setup and usage, of course, such that the user can really go developing and not just setting up tools, right, for all eternity. We're trying to use standard protocols or de facto standards from Microsoft and ARM mostly. And we're trying to be as Rust-friendly as possible. So we're providing cargo plugins. But ProbeRS should really be language agnostic in its core. So the library can be interfaced with FFI, of course, in other languages. And all the cargo plugins could be used as standalone applications too. And if we ever have some time to spare, we will, of course, make this even better by maybe not naming it Cargo Flash, but rather just Flash or whatever the tool's name then is. And we try to actively encourage contribution by having the library on GitHub, such that we really motivate people to contribute to the project. And I try to be as active as possible on Matrix 2, where we have our chat room, so that we can exchange ideas that not one person just defines the entire interface, such that really all ideas can be combined in this one great library. So I've talked a bit about what probe RS can do and what it should be, if possible. But now, let me show you, please, how simple it really is. So let me make a small example. So let us have this imaginary program that just increases a counter at the memory location in RAM. Then let's flash that program. Then reset and halt the CPU to get it into a known state. Then we set the breakpoint after the counter, or at the memory location in flash where the counter will be incremented. Then we wait for the CPU to halt, read the counter, and we repeat the last 2 points such that we can see the counter incrementing, or the counter is incrementing on the target, and we can see it on the host. So first of all, we are acquiring a session. This is just a struct that holds a handle to our probe internally and a handle to our more specific target description. In this case, this is the NRF52. Yeah. So then we're flashing the ELF binary onto our target. We just do this by handing the session to the function, the ELF path, and a format. We could also use a pure binary format or Intel hex here. So we support all three. So this is really convenient. No more magic to that. And then we get a core handle, in this case core 0, because there's just one core on the NRF52. And we reset and halt the core. And then we can already set the breakpoint at this imaginary location in flash where the code resides after the counter has been increased. And then we run the core because, yeah, it's halted at the moment. We wait for the core to be halted again because it will halt once the breakpoint is hit, right? And then we will read one 32-bit word at the location in RAM where the counter resides. So this is really simple and easy. And as you can see, we have control over the entire CPU. So this is really neat because now we have a library which enables us to create any sort of magic tool that can let us inspect our CPU, talk to it, flash any ELF binary, etc. So this is really cool. So a little bit about how the probe RS structure works. I won't go into too much details, but just to give you an overview how this all conceptually works. So we try to have the structure as close as possible to how this actually physically works in like a probe and core sense. So on the lowest level in the probe RS space, so to say, we have the probe drivers. So we provide a trait that is used by the probe struct internally that implementers of a probe can implement. So for the J-Link, for the ST-Link, and for the CMSysTap, we already provide this. But if you were to manufacture your own probe, you could implement a driver for your probe just by implementing this trait. So this should be really easy, and all the internals use this trait then. And then on the next level, we have a core. It works basically the same. We have a trait that you would implement for each and every different architecture. So at the moment, we have ARMv6, ARMv7. I guess ARMv8 is to come soon. And then we have RISC-V. And maybe someone is to implement AVR in the future, for example. And this is really just implementing a trait, more or less. And then we have the target descriptions, which are sort of a better or a more in detail description of all the targets there are. For example, the NRF52-840, which describe the target memory locations and sizes and their flash algorithms. A little bit more about that in a second. And then at the top level, we have the session struct we have seen in the code example 2. It just holds a reference, the probe, and the target description, and it holds core state sort of internally. And you can get a handle to a core by polling the session for the core handle, and then you can control the core from that. So the session is just really a top-level entry struct which manages all state. And then This is basically probe RS. And on top of that, we can build third-party libraries. For example, probe RS RTT, a GDB stop, or our flashing tools. Of course, the flashing tools are inside probe RS because they're commonly used very often, but it's really just building on the layers below. And on top of that, we can build applications. For example, Cargo Flash, Cargo Embed, or our VS Code plugin. So oftentimes people ask me, is this already in Cargo Flash or Cargo Embed, or they issue an issue over there in the repos? But all the functionality is really in probe RS. So if we add a new target or new functionality in general, this will always be in probe RS. So if you install the newest tool and it uses the newest version of probe RS, you get all this functionality. So this is really cool. So it really doesn't depend on the application. So the application is a very thin UI layer that basically just parses arguments and passes them to probe RS. And so I've spoken a little bit about those flash algorithms. So those are ELF blobs that we flash onto the target that, or into RAM that manage the flashing process. And this would be huge work, and also describing all the memory properties of the different targets. We couldn't do all that work, I think, or at least it would take years or many work hours. This is where CMSIS packs come in handy. So this is an ARM standard for target descriptions. So these CMSIS packs contain all the flash algorithms, the target descriptions, and they're implemented by the vendors of the targets. So that means we don't get to do any work, and we still get thousands of available targets. And many of those targets are to be included soon. Yeah, we can just export them. So this is really great that this was done by ARM. So I've talked a little bit about how everything looks like and what it should be optimally. So at the moment, we have a few binary tools, and we have this library that's working great, actually. But of course, we can always extend the toolset. So what's planned next, of course, is a VS Code plugin. So we have a working plugin, but it's very early alpha state. And it uses the Microsoft dApp. This is a modern JSON API for debugger interfaces. And this is implemented in Vim and Emacs 2, for example. And I'm sure it will get into other editors soon, too, just like the language server protocol has been implemented by many, too. And this means we get rid of the entire GDB stack in between. Of course, this means a little bit more work because we have to implement all the debugging things ourselves. But there's cool Rust projects coming up that do this already. So maybe we can tap into that. And as of now, I think we can print the stack trace. We can look at the stack frame, very rudimentary, just pointer values. We can run step and halt and maybe even set breakpoints. I'm not entirely sure how far that is. And you can check it out on GitHub, have a look, try it out, contribute code. It's going to be cool. And then the next thing I have been discussing on the Probe RS channel just minutes before the talk with Brian Cantrill and Adam Grieg too. We're trying to get ITM into master after this weekend. So we're trying to implement this during the Impl days. So for those of you who don't know what ITM is, this is really powerful data streaming on ARM v7 and ARM v8. And it enables you to track interrupt events and memory access events, which then are streamed out in a UART kind of interface. And you can also send custom binary data. So this is really cool for tracing your target in real time because this doesn't use any CPU cycles or additional CPU cycles. So this is around the corner, and there's an open pull request. And there's lots of features coming. I won't go through them for time reasons, but you can find it in the presentation if you scroll down. I will publish that later on. So now for a short demo, because I guess most of you, I mean, sure, the library is cool to use, but most of you are interested in flashing a target or actually debugging a target, right? So we provide two cool binary tools for that. And the first one is Cargo Flash. So I'm here inside the Nordic DevKit repository. And just to show you the structure, it's just a normal Rust project. And Yeah, we can normally we could do cargo run and then dash release and an example blinky. And this, of course, I'm sorry, this of course won't work because we're not having the right target architecture. We also don't have STD, etc. But what we can do is use our in-place replacement. So we just replace run with flash, and we add our chip at the end. This is the NRF52 840, and then we can flash the blinky onto the dev kit I have here with me. I think we can't really see it well, but it shouldn't blink yet. Oh, the camera even does a nice job, so it should flash, and now it should blink. So this is really simple. We have a clean interface, and there's a lot of config flags which we can configure the entire process. And of course, always putting all those flags onto the command line is not really nice, especially when you want to configure the probe or the speed, or you want to have RTT working or a GB server. So we provide a second tool called Cargo Embed. And this is sort of the big brother of Cargo Flash that can also do RTT things, etc. And it really doesn't need any more arguments because there is this Embedded Tome here at the top, which has all those configurations stored. And yeah, so when we run this command, example, I have to put an example, of course, RTT, it should flash the example onto the board and open this RTT console. So we can't really see any output yet, but if we switch to tab 2, we can see what it tells us, that we can type on channel 1 and it will return it to us. So we can type, for example, hello, oxidize. And it will return this in caps. So this is really communication from the host to the target, and it should be really convenient. And we will only expand those tools even more in the coming weeks and months. So this should really provide a nice development experience. So to hop back into the slides. So I've been talking about this debug chain at the beginning of my talk, and the only missing piece here is really the piece in between, so the probe, which has not been done in Rust. But a few folks from the probe RS team, namely Korkin, Disasm, and Adam Grigg, have been really hard at work. And we have this little debug probe here, which operates fully with Rust firmware. And it implements the CMSys DAP debug spec. And yeah, so we have the last missing piece in Rust 2. The probe is extremely fast and very little. And it implements this standard API, so we can also use it with commercial tools, such as ARM Kyle, for example. And it can stream all the things you would need, such as DAP, ITM, and UART data. And you can find it on Korkin's GitHub. The firmware repository has been kept a secret. It will be open sourced on the Probe RS workspace soon. And if you want a probe, just join the Probe RS Matrix channel. We will see that we can get sort of dev kits out in the next few days. We will have to set up some kind of supply chain. So if you want one, join there. I will make an announcement so you can all join in. Yeah, so this was it for my talk. I hope you enjoyed it. You can find us on several places on the internet, our webpage, the GitHub organization, the Matrix channel where we talk a lot, or mostly me spamming. And then, of course, hit us with your questions and bug reports. You're very welcome to report any bugs. And of course, PRs are even more welcome. Yeah, so I guess this was it for my talk. Yeah, if there are any questions, I think I can answer them now. I think we have a few minutes left, not sure.
Yes, there are a couple of questions and a couple of discussions already going on in the channel. And the first question is, when would you want to use RTT versus ITM?
Okay, so RTT is platform independent. The only requirement is really that the core has the capability to let you read memory over the debug interface while it is running. So this is really just two ring buffers in the RAM of the core. which the host and the core access with some safety locks, of course, and they put data and read data from to and from it. So this is platform independent. So you could use it on AVR technically, on ARM or on RISC-V, and also on ARM v6, which misses ITM. The ITM is very proprietary, so to say. It's only on v7 and v8. But what's cool about ITM is that it has those additional tools for streaming out core events, such as interrupts or memory reads and writes, which would use up CPU cycles if you were to do this manually over RTT, so to say. So this is really cool if you don't want to intrude your firmware. But this is a one-way connection. You can only stream data from the target to your host. In RTT, you get both ways. So yeah, those are kind of the differences.
Thank you.
I hope this answers the question.
I guess so. And then there's one other question. With OpenMoCD and a small cargo config, cargo run works as expected. Is there a way to do something similar with cargo flash, cargo embed? So basically, cargo run does everything?
Yeah. I know of a few folks that do this. You can make this happen. It shouldn't be a problem. You can configure cargo flash as your runner, I think. If not, come to the Probe RS channel. We can figure out a solution, I'm sure, because it is possible to use those tools standalone. At least cargo flash, cargo embed misses the flag, I think. But in cargo flash, you can point it to a specific ELF binary. So that works, yeah.